Welcome everyone to Professor Simo again. In this video, I'm going to show you ElGamal Encryption system. So, when we are talking about ElGamal, we are mainly discussing two concepts that we have actually discussed throughout this series, which are public key cryptography within public key cryptography, which is key exchange and encryption and decryption. So, when we are talking about ElGamal, it means that we can send an encrypted message in an unsecured channel where both parties can decrypt and encrypt this message. You see what I mean? Like they can decrypt the ciphered message and encrypt the message in an unsecured channel. So you'll understand more of what I mean when we start with this algorithm. Just know that this algorithm is also related to Diffie-Hellman. Like half of it is based on Diffie-Hellman. So keep your thought process related to Diffie-Hellman. I will be like comparing this crypto system with Diffie-Hellman, such that you would be like, okay, so this is how it was done in Diffie-Hellman. This is how it's done in ElGamal. I would recommend you guys watch the Diffie-Hellman video first if you want to like understand more about what exactly key exchange is. You see what I mean? So let me start with this protocol. Okay, so we start with the two parties should agree on two variables, which are alpha and q, where alpha is a large prime number and alpha is a primitive root of q. What does that mean? It would, or like, how does that help us? Okay, first let me draw this first. Okay, assume we have alpha power of k mod q. Okay, if alpha is a primitive root of q, we would have a larger set of unique numbers or unique patterns. To understand and see this visually, let me show you this table. Assuming we choose our alpha as 7 and our q as 19. So if we take 7 to the power of 1, 7 to the power of 2, 7 to the power of 3, till 7 to the power of q minus 1, which is 18, mod 19, mod 19 again, mod 19, mod 19. Here, if alpha is a primitive root of 19, it would mean that the answers are all going to be unique, or the pattern throughout which we'll get would be unique. If we look at this table, if we choose 7 as our alpha, we will be having 7 to the power of 1 mod 19 is 7, 7 to the power of 2 mod 19 is 11, 7 to the power of 3 mod 19 is equal to 1. Look here, 7 to the power of 4, it's 7 again. 7 to the power of 5, 11 again. 7 to the power of 6, 1. See, 7, 11, 1, 7, 11, 1, 7, 11, 1, 7, 11, 1 again, 7, 11, 1 again. You see what I mean? Here we're looking at a pattern. So we are just limited into 3 options. Imagine, we're just limited to 3 options. Whereas if alpha is actually a primitive root of 90 of q, for example, 2 is a primitive root of 19. 2 to the power of 1 mod 19 is 2. 2 to the power of 2 mod 19 is 4. 2 to the power of 3 mod 19 is 8. And so on. As you can see over here, there are no patterns. It's all unique. So what does that mean, or how does that help us? Mainly, it would increase the size or the limit of options we will be having. Okay? Now that we know why we choose alpha, or why do we emphasize on alpha being a primitive root of q, we have seen it. Okay, now we go to the next step. After we agree on an alpha and a q, we will go to generating the keys. Here Alice will generate her keys. So what will Alice do? We already agreed on an alpha and a q. Now Alice will create her public key. So to create her public key, Alice, what she will do is take the alpha to the power of her private key, which is xa mod 19, mod q. Of course, alpha will have a private key and a public key, but we also, okay, so what is public for us? What will be public is the public key, of course, the alpha and the q. except the private key. It should not be shared, it should be private. So now, Alice has declared her public entities or public variables. Bob will come and will want to send his message. So Bob's message has to be within the set of 0 and Q minus 1. Okay? Such that when we talk about modular arithmetic or modular exponentiation, as we can see over here, okay, when we talk about the concept of modular arithmetic, it would mean that y, or the public key, is within Q, like it's less than Q, or like within the range of 1 and Q, 0 and Q. You see what I mean? Don't emphasize on that. Don't. Going next is going to encrypting the message. Okay. So Bob again has message M. Message M is between 0 and Q minus 1. Now Bob will want to generate some random number K, where K is also less than Q. Okay. M is less than Q, and K, small k, is less than Q. Bob now will start with generating the shared secret key using Alice's public key to the power of his small k mod Q. Again, when we talk about ElGamal, it's based on Diffie-Hellman. Assume the k is like the private key of Bob in Diffie-Hellman, you see what I mean? Such that you don't like get confused, okay? So now we go to creating C1. So a lot of students get confused when we're talking about what C1 actually is. Again, when we talk about Diffie-Hellman, here, C1, assume it's like the private key, okay? Assume it's the private key of Bob. So how do Bob generate the private key? Again, just use alpha for small k mod Q. Assume this is the private key of Bob. Not complicated, صح? Yeah. Now we have C2. So what would be C2? C2, assume it as the ciphertext. So we'll take the SK time the message mod Q. So if we look at this point of view, where C1 is the private key, sorry, C1 is like the public key of Bob, and C2 is the ciphertext. To be very simple, I think I made a mistake saying that this is the private key. I'm sorry. This is like the public key of Bob. Okay? And this is how we generated the public key. Looking at Diffie-Hellman, this is how you generate your public key, right? So this is just like the public key of Bob. And this is the ciphertext. So now, Bob will send to Alice the following. And it will be public, by the way, okay? Alice, take C1 and take C2. Let's talk about the security of ElGamal real quick, or should we leave it at the end? We can discuss it real quick right now, okay? So when talking about ElGamal, one thing we have to look at is how we are sharing this on an unsecure channel, for example. Right? Maybe even if it's a secure channel, no one can know the secret key. But why can't anyone know the secret key? Because of the discrete logarithm problem. The discrete logarithm problem says, if I know the public key, the alpha, and the Q, I will not be able to find the private key. Here, if I know the public key, the Q, even the SK, I will not know the private key. See here, alpha, Q, C1, I still can't know the private key. This is called the discrete logarithm problem. And because we are using modular arithmetics, we will be able to get the message after multiplying it by SK. We will see that in the decryption process. Let's go to the decryption process real quick. So we know C1 and C2 are my public parts. Now Alice will take C1 and C2. What will Alice do? She will first use C1 to get the SK. Again, we said assume C1 is the public key of Bob, right? So we take C1 to the power of her private key mod Q. Then, now that we know SK, see, we have SK here and C2, right? So, what modular arithmetic say, or modular multiplication says, if I have a number, if I multiply it by its, like showing here, if we have SK, for example, and we take its multiplicative inverse and multiply them with each other, we would get 1. You see what I mean? So here, the message is equal to inverse of SK times M mod Q, and because the multiplicative inverse, we will be able to find the value of M. So we can even prove how SK is the same for both. So what is the value of S1? We come here to the right. Sorry, C1. C1 is equal to private key, small power of K. Okay. All multiplied, all to the power of Alice's private key mod Q. Here we have alpha K XA. This is the value that Alice and Bob will be sharing, as you can see over here in the SK. In the SK here we have Alice's public key, which is equal to this part. To the power of K will be this whole part. Again, if you scroll down again, we look at the SK here with Alice, replacing C1 with the alpha to the power of K multiplied by Alice's private key, we can see how they both share the same secret key. And by having this secret key as like the number, we just use its multiplicative inverse or modular multiplicative inverse, multiply it with the here we don't multiply it with the M, multiply it with C2, multiply the inverse SK with C2, and basically you will get M. Thank you for watching, and I hope you have learned in this video how to encrypt, decrypt, exchange keys using ElGamal. Thank you everyone for watching.